Hello, Mr. Luong. This is my FRQ practice 3. So for part A, I'm going to draw the torque graph first. And I'm going to draw the constant line because I know torque is constant due to how torque is tension times radius. So the tension is constant, therefore making torque constant. And the tension is constant because it has to oppose the force of weight of the mass, hanging mass, and since hanging mass, the weight of the hanging mass is constant, and you need to have constant acceleration, so then that's why the tension makes the tension is constant because weight of the hanging mass is constant. So that's why net torque is constant, and since net torque is the derivative of angular momentum, the angular momentum is going to be increasing with a constant slope because, like I said before, net torque times time equals a change in angular momentum. So when you divide it by time, you're going to get torque. And since I said torque is constant, when you divide angular momentum by the time, so that like that, you divide angular momentum, change in angular momentum over change in time, change over angular momentum over change in time, it's going to be a constant slope. And kinetic energy equals to 1/2 mv squared. Since it's a square, it's going to look like a parabola. And initially, the bicycle wheel was not moving, so that's why there was no kinetic energy in the beginning. And for part B, the momentum graph is going to look like a line with a constant slope because P equals mv, and m velocity is increasing at a constant rate due to how acceleration is constant. So that's why velocity, the momentum graph is gonna be linearly because its slope is a constant. And the potential energy graph is gonna look like this, like a parabola. And there's gonna be initially there's gonna be potential energy because the hanging mass is has a certain height above the ground, so that's why there's initially potential energy. And then when it reaches like 5 seconds, it's already like near the end, like near the ground, so that's why there's maximum velocity, which means there's maximum kinetic energy. And when that happens, there's no more potential energy because what is lost in potential energy is gaining kinetic energy. So that's why the graph for kinetic energy is going to look the opposite of potential energy. This graph looks the same as the kinetic energy graph for the bicycle wheel because they both have the same velocity, just different mass, and they're both square, so that means it's a parabola, and the hanging mass was initially at rest as well. So the kinetic energy versus velocity graph, it's going to look like a line with a constant slope because kinetic energy is 1/2 mv squared. And when you divide it by velocity, it's just gonna be 1/2 mv. So essentially, this graph is basically looking like the momentum graph, but it's just 1/2. So that's why it like mirrors the momentum graph because the velocity is increasing at a constant rate due to how there's constant acceleration. And for part, am I recording this? Okay. For part C, I know the angular velocity at 5 seconds. So I need to find that. So angular velocity at 5 seconds is 10 spokes per second. Since it's spokes, I need to convert it to radians per second. So angular velocity at 5 seconds is 10 spokes per second. When you convert that, I know 16 spokes make up 1 rev or revolution, and then 1 revolution is 2 pi rad. So when you simplify everything, you're gonna get angular velocity at 5 seconds is gonna be positive 3.93 rad per second. And for part D, to find the angular velocity, I need to find the slope of this graph. So I'm gonna use these points, 2 and 0, and the time at 1 second. So the slope of the angular velocity graph is going to be the angular acceleration. And since it's increasing at a constant rate, the angular acceleration is going to be constant. So that's why I can use any point. So I'm going to use these points. So then angular acceleration equals to change in angular velocity over change in time. So that expands to that. And this is 0 because initially it was at rest. So then the final angular velocity at which I used at 1 second was 2. So this is going to be 2 spokes per second square, but you want that in radians per second. So I just did the same thing I did before to when I found angular velocity to change it to rad per second. So when you do that, you're going to get 0.79 rad per second square. And I know acceleration is radius times angular acceleration. So I just plug in the radius, which is 0.3 when you convert 30 centimeters to a meter. And then angular acceleration is 0.79. So the acceleration is going to be 0.24 meters per second square. Wait, am I recording? Okay, good. Okay, for part E, I'm going to use the net force formula for the mass, which is 50 gram, but when you convert it to kilogram, it's going to be 0.05 gram. 0.05 kilogram. Yeah, so 50 gram to kilogram is 0.05 kilogram. So that's what I'm going to do to plug in for the mass and the tension. And you do the weight of the mass subtract the tension because the mass is like the downward force and tension is opposing it. So then you just equal MA, and then mass is 0.05 times gravity. And I'm going to subtract mass times acceleration to the other side. And mass is 0.05 times acceleration equals t. You take out the 0.05. Gravity subtract acceleration, which is 0.24 from the previous problem I got. So now tension is going to be 0.48 Newton. For part F, I know net torque is going to be the force perpendicular to the radius. And the force perpendicular to the radius of the bicycle wheel is going to be the tension. So tension times radius. And the tension, I'm going to use the tension I got from the previous problem, which is 0.48 times radius is 0.3. So the net torque is going to be positive 0.14 newtons times meter. And it's positive because the bicycle wheel and the hanging mass are both going like counterclockwise. Yes, so that's why it's positive, because it's going counterclockwise. And then for part G, I know net torque equals to tension times radius, like I said before, but net torque can also equal to moment of inertia times angular acceleration. So since they both equal to torque, net torque, I can set them equal to each other. So since I set them equal to each other, I can divide both sides by angular acceleration to find the moment of inertia of the system. And now just plug in everything I know. Tension is 0.48, radius is 0.3. Angular acceleration, which we found before, was 0.79. So now the moment of inertia of the system is going to be 0.18 kilogram times meter squared. For part H, I'm going to use the moment of inertia of the system I found before to get the mass of each spoke. So moment of inertia of the system is going to be mr squared. And this is the moment of inertia for the wheel, which is considered a hoop, I guess, or a ring. And the moment of inertia for a hoop or a ring is mr squared. So that's why I did mr squared. And then for the moment of inertia of the 16 spokes, you're going to have to multiply 16 by the moment of inertia of each spoke, which is 1/3 ml squared. And the length is the radius because, yeah. So then you multiply the moment of inertia of each spoke by 16 to get the total moment of inertia of the 16 spokes. And the mass is m/48 times length square, which is radius square, because the radius is the length of the spoke. And you use 1/3 because that is the coefficient of the moment of inertia when there's a rod and the pivot is at the end of the rod. So now I just simplify. This is going to become 9. So then I system is, and this is going to be 9/9. So 9 over 9 plus 1 over 9 is going to be 10 over 9 mr squared. And now I multiply both sides by 9, divide both sides by 10r squared to get the mass of the wheel. And this is the mass of the wheel. And mass W is for mass of the wheel. And 9 times moment of inertia of the system is 0.18 over 10. The radius is 0.3 squared. So now the mass of the wheel is 1.83. And you want the mass of the spoke. So I know MS is for mass of the spoke. I know they said M over M wheel over 48 equals to the mass of the spoke. So I just plug in 1.83 over 48. And now that is going to be equal to 0.038 kilogram. But you want this in grams. So now you just multiply that by 1,000. Because 1 kilogram is 1,000 grams. Now the mass of each spoke is going to be 38.06 grams. Okay, for A, B, C, D, F, G, H, I. Yeah, part I. I'm going to use the graph to find angular velocity at 30 seconds. So at 30 seconds, there's 6. And now I'm going to just convert that to radians per second like I did before. And you divide it by 16 spokes, multiply by 2 pi radian to get 2.36 rad per second. And now I'm going to find the velocity at 30 seconds as well, because I think that will make it easier to find the total kinetic energy of the system. Which is, and I know, velocity is equal to radius times angular velocity. So then you just plug in what you have for radius and angular velocity at 3 seconds, which is 2.36. So now velocity is going to be 0.71 meters per second. Okay. So then kinetic energy of the system is 1/2 mv squared. And this is going to be the translational kinetic energy for the hanging mass, because there's linear kinetic energy for the hanging mass. But you do 1/2 I omega squared for the bicycle wheel for the bicycle wheel, because there's rotational kinetic energy for the bicycle wheel. So then now you just plug in everything you know. And the mass of the hanging mass is 0.05. The velocity, which we found right here, is 0.71 squared plus 1/2. Total moment, the moment of inertia of the system is 0.18. And then the angular velocity is 2.36. So then when you simplify everything into the or you plug it into the calculator, you're going to get the total kinetic energy of the system equal to 0.52 joules. For part J, I know I'm going to use the net torque. I'm going to set net torque equal to each other again. But for part J, there's going to be tension 1 and tension 2. And this one is going that way. This one is going this way. So I need to do tension 1 times radius, subtract tension 2 times what is it? Yeah, tension 2 times the radius, because that's the net torque for this new system. So tension 1 times radius minus tension 2 times radius equals to moment. You're going to have the same moment of inertia of the system because the wheel doesn't change. And you're going to also have the same angular velocity, because that's what I think the problem said, right? Yeah. It has the same angular speed versus time graph, so that's why it's also going to have the same angular acceleration. And the angular acceleration we found before was 0.79, I think. Yeah, 0.79. So that's what we know. And now I'm just going to substitute T1 and T2 into the equation. Actually, I'm only going to substitute T2. So let me just move I system times angular acceleration to the other side. And add tension 2 times radius to the right side. So I know tension 1, or now in order to find tension 1 and tension 2, I need to set up the net force equations for each tension. So for the tension 1, the opposing force is the mass of the 70 gram mass, and 70 gram to kilogram is 0.07 when you divide 70 by 100. So that's why I'm going to 0.07 times gravity, subtract T1 because the T1 is opposing the force of gravity, equals 0.07a. You move 0.07 minus 0.007a to the side, and I'm going to take the 0.07 out, so you're going to be left with g minus a equals T1. And then for T2, I know T2 minus mg, which is the unknown mass, the m, and now you just add mg to the side, take out the m because you want to find that. So now I just plug in tension into right here. So 0.07 g minus a times radius minus I cis into the solution T2 times r. Divide everything by r to get T2. When you put in all your known values, and angular acceleration was 0.79, radius is 0.3, and then acceleration is 0.24. So to get T2, and after that, T2 is going to be 0.19, but I know T2 equals to ma plus g, so I divide a plus g to get mass. So T2 is 0.19, a is 0.24, plus 9.8 to get the mass, and the mass is going to be 0.019 kilogram, but you want this in gram, so 1,000 kilogram. 1 kilogram is 1,000 gram. So then when you do that, you're going to get 19.06 gram, which is the mass of the unknown mass of the unknown object. And am I still recording? Okay. For part K, I know I'm just gonna plug in what I got. I'm just gonna plug in what I know for tension to get the tension 1, which is the string on the left side, to compare it to the tension in the previous system. Tension 1 is gonna be right here. So 0.07, 9.8 subtract 0.24. So tension 1 in the new system is 0.67 Newton. And the tension, since this tension, 0.67, is bigger than the tension we got on the previous system, which is 0.48, the tension in the left string will increase. And this makes sense because since you have a bigger mass, it's going to need a bigger tension to oppose it so that you have the same constant acceleration. And it also makes sense because this tension needs to be big so that it can oppose the tension on the other side, so that the system has the same acceleration when there's only one tension. Yes, okay, I think that is all. Thank you, Mr. Luong. Bye-bye.